Hey everyone and welcome back to the channel. Today we're diving into one of the most fundamental data structures in computer science, the trees. In the last video we already learned a bit about trees and now we want to look how they could work in code. So we're going to explore the core concepts of trees, especially binary trees, and then get hands-on with Java code to understand how we traverse them. That is how we visit every single node in our tree. We also touch upon the power of generics in Java, which makes our tree implementation very flexible. So let's get right into it. While there are many types of trees, today we'll focus primarily on binary trees. A binary tree is a special type of tree where each node can have at most two children, a left child and a right child. Even more specifically, we often work with binary search trees or BSTs. What makes a BST special is an order property. For any given node, all values in its left subtree are less than the node's value, and all values in its right subtree are greater than the node's value. This property makes searching for elements incredibly efficient. First, let's look at how a tree node could look in Java. Before we dive into the implementation, let's talk about something crucial in our Java code, the generics. You'll see this T in our class definitions. The T stands for type and it's a generic. The generics allow us to write classes and methods that work with any type of object, providing type safety at compile time. Without generics, we'd have to use objects as the data type for our nodes. While this works, it means we'd constantly have to cast objects back to our design type, for example integer or string, leading to potential class cast exception errors at runtime. So with generics you can create a binary tree of type integer, and the compiler knows that all data within the tree must be an integer. This prevents runtime errors and makes our clone cleaner and safer. You might also notice T extends comparable with type T. This is a bounded type parameter. It means that whatever type T is, it must implement a comparable interface, because for a binary search tree you need to be able to compare data values. For example, we need to check if 5 is less than 10, and for this we have the compare2 method from the comparable interface, which provides us exactly this functionality. So let's start with the TreeNode class. We have three main fields, data of type T, left which is a reference to its left child, and right which is a reference to its right child. The constructor simply initializes the node with the given data and sets both left and right children to null initially. And also we have the getter and setter for every attribute. Then we have the binary tree class itself. The binary tree class holds a root node. This root is the entry point to our entire tree. Then we have the insert method. The insert method is how we add new elements. It's a public method that calls a private helper insert recursive, and the insert recursive method is the core logic. It's a recursive function that takes the current node and the data to be inserted. We have the base case if the current node is null. In that case it means we found an empty spot, so we create a new tree node with the data and return it. Then we compare the data to the current data using compare2. This is the method we get from the comparable interface. If the data is less, we recursively call insert recursive on current left, so we go to the left subtree, and if the data is larger we go to the right subtree. The assignments here with current point left or current point right are crucial because it updates the parent's reference to its child after the recursive call returns a new node, and in the end we return current. Searching for an element in a binary tree is very efficient. It's similar to binary search in a sorted array thanks to the BST property. Again we have a method search, and the method returns a boolean, so we get true if the node was found and false if the node was not found. And again we call a recursive function. In the recursive function again we have the base case if the current node is null. This means if we explored a path and didn't find the data, else we compare the search data with the data of the current node, again with the compare2 method. And by the way, I forgot to mention that the compare2 method returns an integer. If the two elements we compare are equal, it returns 0. If the target data is smaller, we return -1, and if the target data is larger, we return 1. So if comparison equals 0, we found our element. Otherwise, if it's smaller, we search in the left subtree, or if it's larger, we search in the right subtree. This halves the search space at each step, which makes it very fast. Deleting a node from a binary search tree is the most complex operation, as we need to maintain the BST property and ensure the tree remains valid. There are three main cases to consider. Again we have our delete method and call a recursive method, and here we have the base case again. If the current node is null, the data isn't in the tree, so we can return null. We have to find the node we want to delete, so we traverse left or right based on the comparison with data, just like search or insert. So the else if and else clauses are exactly like before. Once the node is found, if comparison is equal to 0, we have our three cases which I mentioned before. We have case 1 if node is a leaf node, so we have no children. This is the simplest case. You can simply return null to its parent. effectively removing it from the tree. In case 2 the node has one child, if current.left is equal to null, it means the node only has a right child, so we replace the current node with its right child, and if the node only has a left child, we replace it with its left child. And case 3 is when the node has 2 children. To maintain the BST property, we can't just remove the node. We need to find a suitable replacement for the node. The common strategy is to find the Inorder successor. This is the smallest node in the current node's right subtree. For this we use our find smallest value helper function. This function is searching for the node with the smallest value, which is always the leftmost child. So what we do is, if there is no left child anymore, we return the data of the node, or else we call it recursively on the left child. Then we copy the data of the successor to the current node, which is the one we want to delete. And finally we call delete recursive on the right subtree to remove the original successor node and return the current node. This way the tree structure is preserved and the BST property holds. Now we can continue with the traversal methods. Traversing a tree means visiting each node in a specific order. There are 3 primary ways to traverse a binary tree: Inorder, Preorder and Postorder. All of these typically use recursion, which is very natural for tree structures. The first traversal is Inorder traversal. So we have the base case if node is null, so we do nothing as there's nothing to traverse. Otherwise it recursively calls itself on node.left, so the left child of the node. This ensures we go as far left as possible. Once the left subtree is fully processed, it then prints the root itself, and finally it recursively calls itself on the right child. For a binary tree, Inorder is special because it visits node in sorted order. This is incredibly useful if you want to get all elements of your BST in ascending order. Preorder looks the same, only this time we print our root first, then visit the left subtree and then the right subtree. Preorder traversal is useful for creating a copy of a tree or for expressing the structure of a tree, often seen in parsing expressions or file systems where the parent directory is processed before its subdirectories. And Postorder as well. This time we visit the left subtree, then the right subtree and then the root. Postorder traversal is commonly used for deleting a tree from memory to avoid so-called dangling pointers, or trying to access memory that's already freed. It's also used in some parsing algorithms like evaluating expression trees. We can also implement these methods iterative instead of recursive. For this we use a stack, so we initialize the stack and start by pushing the root onto the stack, and while the stack is not empty, we pop the node from the stack and visit it, then we print its data, and then we push the right child onto the stack and then the left child. The reason for that is that stacks are last in first out, and we want to visit the left child before the right child. So we push the right child first so the left child is on the top of the stack and gets popped and processed next. The iterative approach avoids recursion and can sometimes be more efficient in terms of memory usage, especially for very deep trees. And finally we also have Levelorder. Levelorder prints all nodes level-wise, from left to right, so this time we use a queue. We start by enqueuing the root, and then while the queue is not empty, we dequeue the front node and print its data, and then we enqueue its left and right child if they exist. And we need the queue to ensure that the nodes are visited in the correct level-wise order. So let's see all of this in action with a main method example. If I run this, we can see our insert method builds the tree, respecting the BST property. Our traversals provide the different ordered views of the tree's content. We can also efficiently search for elements, and delete handles different node types gracefully, always maintaining the tree's integrity. I've tested all different cases here, and they all worked how it's expected. And with the help of the generics, we can also use different data types for our binary tree. For example, we can have a string binary tree. First I inserted some nodes with strings as their value, and we can also traverse the tree, search for elements or delete elements. For example, they are used for databases and dictionaries, because BSTs are fundamental for efficient data storage and retrieval in databases, and for implementing dictionaries or maps, allowing very fast lookups, insertions and deletions, with an average time complexity of big O of log n. They are also used in file systems, because hierarchical file systems are often represented as trees. Also compilers and interpreters use trees, the so-called abstract syntax tree, to represent the structure of code or mathematical expressions, which are used in machine learning for classification. And that's a wrap on our deep dive into trees and their operations, and how to implement their core operations inserting, searching and deleting, as well as the different tree traversal methods. I hope this video helped clarify this crucial data structure. If you found this helpful, give it a thumbs up and subscribe for more content. Thanks for watching and see you in the next video.